Hi everybody, this is your last video in section 1 of unit 3 on normal distributions. So in this one, I'm gonna go over officially, like formally, transforming data and what that does to different statistical measures like center, shape, spread, etc. Okay, we have talked about this in class already. You have seen this in class already, but I am going to talk about it more officially. And then I'm going to show you how to connect those things to, oops, sorry. I'm going to show you how to connect those things to what we talked about in the last video, which was z-scores. Okay, so let's go ahead and jump into it. So, first, right, make sure that you know, right, that you have, okay, so mean, standard deviation, and variance all have these very long and kind of complicated formulas, right? The good thing about this is that you do not have to memorize these formulas. They will be given to you on the formula sheet that you get when you actually take the AP test, okay? So remember, mean is just average. Standard deviation is the average distance a data point is away from the mean. And then variance is standard deviation squared. Okay, so when we go and transform data distributions, right, there's a lot of things about the data distributions that will change, right, when you manipulate them, when you do certain things to them. Okay, so just as a reminder, okay, when you add or subtract a constant, that only will affect, whoops, my pen went a little wild there. Okay, so that will only affect your center, individual data point, and individual data point locations, right? So if you take a constant and you add or subtract a constant to your whole data set, right? You're essentially taking your data set and you're moving it along the x-axis, right? Either moving it to the right if you're adding a number, or if you are, or moving it to the left if you're subtracting a number. So that means the center will change, right? It will move the exact same distance that you added or subtracted, right? As will individual data location. So that's like percentile values, or like individual quartiles, like the actual locations of those things, right? A quartile will still be like quartile 1 is still at the 25% mark. Like it's still, yeah, at the 25% mark of the data, right? Meaning that 25% of the data is below that value. It's just where that location is will get shifted, okay? But the shape, spread, and variance are not going to change, right? If all I'm doing is moving the distribution to the left or to the right on the x-axis, right? It's not going to change my shape, right? I'm not making it wider or skinnier, right? So my spread and thus my variance are not going to change. But if you multiply or divide by a constant, everything changes except for shape. Okay, so when you're taking a distribution and you're multiplying it by something, you're essentially taking it and you're either enlarging it, or if you're dividing it, you're shrinking it, right? Which means that the center will move, each individual location will move. Okay, if you're multiplying it, the spread is going to get larger. If you're dividing it, the spread is going to get smaller, because it's like you're basically taking your, like the shape of your distribution and blowing it up, making it larger, or shrinking it and making it smaller. Okay, but the shape is not going to change, right? I'm not taking a normal distribution like a bell curve and changing it to something that's skewed, right? Multiplying and dividing is not going to do that. Just as a reminder, right, for variance, you end up multiplying or dividing by whatever the constant was squared, because variance is standard deviation squared. Okay. Then when you take two distributions, right? Like two data distributions, and you add them or subtract them, okay? You add or subtract the location and the centers. Um, if the distributions are similar shapes, then their added or subtracted distributions um, should be similar shapes. Like the shapes should stay the same, but we just say it varies because it will. It depends on the individual like problem, what's going on with that data distribution. Okay. Like if you take two distributions and one that's really skewed to the left and one that's really skewed to the right, and you add them together, right? So say you have a distribution like this that's really skewed to the left, and then another or skewed to the right, and then another distribution that looks like this. If you add those together, the new distribution that you have is actually bimodal, right? So shape tends to vary, okay? And we just say that the spread will increase when you add or when you subtract distributions, right? Because remember, when you're combining distributions in any way, you are increasing the variability, right? You're taking one distribution that has variation in it, and you're adding or adding negative values with, which is like what you would say if you're subtracting, right? And you are combining them. You're taking like a small amount of variation and a small amount of variation, and combining them, you're going to end up with a larger amount of variation. Okay. But the biggest thing to remember when you are adding or subtracting distributions, okay, so like these bottom two here, is that you always, always, always add variances. Never add standard deviations. Okay. The reason why is like kind of beyond the scope of this course. Just trust me, like it doesn't work. Just because of the way that standard deviation is calculated. Okay. So you always add variances. And then if you want to figure out what your new standard deviation is, you would have to add add the variances and then take the square root of your new variance to find a new standard deviation. Okay, so let me clear my screen off. Let me pause this really quick, clear my screen off, and then we're gonna try a couple as an example here. Okay, so in this example, we have, let me switch this over. We have temperature data that was measured in Celsius, and then we have this information about it. So we know that it was a sample size of 30. Gave us mean, standard deviation, and then the 5-number summary: minimum, quartile 1, median, quartile 3, and maximum. Okay, so this is in Celsius. So this says first to find the mean temperature in Fahrenheit. Okay, so remember that mean, right, is affected by both adding or subtracting a constant and multiplying or dividing. Okay, so both of these values, the 9/5 and the 32, is going to affect my new mean. Okay, so all I'm going to do here is say wherever I see a C, I'm going to plug in what my original mean was in Celsius to convert it to Fahrenheit. So the mean in Fahrenheit is 9/5 times the mean in Celsius, which is 8.43. Okay, this is the mean in Celsius, okay, plus 32. And then you just have to go through and calculate that. And when you do, you get 47.174 degrees. So the mean temperature in Fahrenheit is 47.174 degrees. Okay. Now, standard deviation is going to be a little bit different. Right? Standard deviation will be different because standard deviation is a measure of spread. Okay, and standard deviation is not affected by adding or subtracting a constant, but it is affected by multiplying or dividing a constant. Okay, which means that in my original equation, right? Fahrenheit equals 9/5 Celsius plus 32. Okay, this is the only part that's going to affect the standard deviation. This will not affect standard deviation. So my standard deviation in Fahrenheit is 9/5 times my standard deviation in Celsius, right? My standard deviation in Celsius, if I go back up to the top here, is 2.27. 2.27, right? And you just have to go and multiply that through, okay? And you get 4.086, okay? And then the last part of this is it says interpret this value in context. So if you remember, the way that you interpret standard deviation in context is it's the average difference or the average distance away from the mean. So you would say on average, the temperatures, or you would say on average, the difference between the individual temperatures, I really cannot spell today, and the mean temperature is, and I'm going to say approximately 4 degrees, right? Approximately 4 degrees Fahrenheit. Move this up so you guys can actually see that. Okay. All right. Then the last question here is, it says the 93rd percentile, turn this back on, the 93rd percentile of readings was 12 degrees Celsius. Okay. So they want to know what the 93rd percentile is in degrees Fahrenheit. So look, a percentile, like where the actual location of the percentile is affected just like mean by adding and subtracting and multiplying and dividing. So this right here, the 12 degrees, that is my percentile location. Okay, so I want to figure out where the new percentile location is in Fahrenheit. So my percentile, and I'm going to label it with a lowercase p, in Fahrenheit is 9/5 times the percentile location in Celsius, which is 12 plus 32. Okay, and then when I work all that out, I get 53.6 degrees. Okay, so this is the 93rd percentile. In Fahrenheit. Okay, so that's it for just basic data transformation. We'll do more with adding and subtracting distributions when we get into our unit specifically on probability. So that's unit 5. So we'll get to that in a little bit. Okay, so give me a second. I have to reset my screen here because the last thing I'm going to talk about in this video is I'm going to try to tie everything that we've been talking about together. So z-scores from the past video and this idea, the transforming distributions, and introduce the idea of the standard normal curve to you. Okay, so give me just a sec to clear this off. I will be back momentarily. All right, y'all. So here we are at the end of this video. We're going to try to tie everything together. Okay, so in the last video, I told you about z-scores, okay, where you take an x value, a data point, subtract the average, and divide by the standard deviation, okay? In the earlier part of this video, I talked about adding and subtracting constants and dividing and multiplying by constants, okay? So in the actual z-score formula, which, if you remember, is z equals x minus the mean divided by the standard deviation. Okay, what you have going on right here is you're subtracting a constant, right? Because the average is going to stay the same for every data point in the distribution, okay? And you are dividing by a constant in the standard deviation, okay? So it's exactly the same as what we just did, right? So we're essentially, when we calculate a z-score and when we standardize things, essentially what we're doing is we're taking our original data set and we're transforming it by moving it, right, up or either to the left or to the right on the x-axis, right? We're going to move it, and then we're also going to either enlarge it or shrink it, right, depending on whatever the standard deviation is. Okay, so when you subtract a mean, what you're really doing is you're subtracting a constant. Okay, because no matter what, for every data point in the distribution, the mean will be the same. Okay, right? What that does, right, what you're actually physically doing is you're essentially shifting, right? So it shifts the original distribution, x bar, right? And when I say x bar, I mean, turn this on. X bar is this symbol right here. X literally with a bar over the top of it, right? That's your symbol for average. Or remember, I called it that kind of weird looking fancy U symbol, mu, okay, in the last video. Okay, so you're essentially taking your original distribution and shifting it that many units to the left because you're subtracting, okay? Dividing by a standard deviation is just dividing by a constant. Okay, so essentially what you're doing is you're either shrinking, so it shrinks or enlarges the original distribution. Did I spell that correctly? Yes. Or enlarges the original distribution um, by the factor s, right? Remember that is that's standard deviation. That's the symbol for standard deviation, right? S is the symbol we use for standard deviation. Or you saw me call it and use that fancy Greek symbol, sigma, in the last video. Okay, the reason I used that is because we were dealing with a population value. Okay, so essentially, right, you're dealing with a lot of the same formulas, okay, in when you're talking about a z-score, just you're plugging different values in, okay? So you're literally converting an x value, a data point in a distribution that we don't know a lot about, to a z-score, which falls into a distribution that we do know a lot about, okay? But in general, what you're doing, right, when you calculate a z-score is this. You're taking your data points or your sample value, right, the value that you want to know more about, subtracting the average or the true value, okay? Because remember, our goal here in statistics, right, is to search for the truth, okay? And you're dividing it by a standard deviation. Okay, so then when you go and do this, you may be thinking, okay, great, like that kind of makes sense, but like, why am I doing this? Like, why do I have to convert my data to a z-score? Okay, so what's the point, right? And the whole point of using a z-score, right, and standardizing your data is so that you can fit your data to something called a standard normal curve, okay? So the goal is to fit your data to a standard normal curve, okay, right? Or you sometimes you'll hear it called a standard normal distribution. Same thing, okay? So here's why we do that, okay? We don't know a lot about a lot of distributions of data that you see out in the universe, right? That can occur out in the universe, right? It's very difficult. Analyzing data is actually very, very difficult if you don't have the right tools with which to analyze the data, okay? So there are a lot of distributions in like when you go and gather real data in the real world, there are tons of distributions that look like a normal curve, meaning they look like a bell curve, right? They look something like this, right? Where you have the center kind of here in the middle, right? And then it has a certain amount of spread, right? Most of the data lives in the middle of the distribution, right? And then you kind of have the two tails out on the outside, right? On the left and on the right. It's symmetric, right? There's a ton of data out in the world that falls under or looks like a bell curve, which is great, okay? Because normal distributions and bell curves are a lot easier for us to analyze and to calculate things about, just because statisticians have spent so many years studying normal distributions. Okay, so our life is a little bit easier when our data fits to a normal distribution. But there are so many possible normal distributions out in the world, right? You can have some that have a really, really large spread, um, and are kind of like really long, but maybe short. They still look like a bell curve, but maybe they're, let me switch my pen. Maybe they look, um, maybe they look more like this, right? That's a bell curve. That's a normal curve. There's others that you'll see that, um, you know, still a bell curve, right? But are very short and like they take up very little X space, but are very tall, like kind of skinny and tall, right? There's others that that kind of look more like what we're used to seeing, right? More like a typical bell curve, right? So there's an endless number of distributions, right? Of normal distributions, depending on the data that you have. Okay, there is one normal distribution that we know a lot about, and that is the standard normal curve. Okay, so this distribution, this specific normal distribution, the standard normal curve, is the one that we know the most about. So what z-scores allow us to do is they allow us to take all of these crazy looking bell curves and convert them to something that we know a lot about, right? We're literally standardizing them, okay? We have lots of tools, right? Like our calculators, right? And there's some tables that you can use in order to figure out probabilities and how likely something is to occur within that distribution, with the standard normal curve that you don't have with other bell curves, right? So what z-scores allow us to do is, if we are taking all of these distributions up here, right? And they're on the x-axis, right down here at the bottom. These are all x-axes, right? These horizontal axes. Okay, same thing you can see down here. Okay, what z-scores do is they convert x values to z values. Okay, so we're essentially taking our distribution and changing it to a z distribution and converting it to the standard normal. And the standard normal curve has always has the same mean and the same standard deviation. It has a mean of 0 and a standard deviation of 1. Okay, so over on the right hand side here, if you're following along with notes there, that the mean of the standard normal distribution is always 0 and the standard deviation is always 1. Okay, now you'll see there's two like versions of the z-score formula that you see both in your notes and on the screen. Okay, where you have this equation for samples, right? And then you have this equation for populations. Okay, so remember, this class is called statistics, right? Um, and the reason it is called statistics is because parameters, right? These things, right? These fancy Greek letters, these are technically called parameters. because they're talking about it's the truth, right? It's the true average, the true standard deviation for the entire population, right? That would be when we're able to do a census and we're able to gather information from every member of the population to get the actual true average and the actual true standard deviation. So because those are true values, they're parameters, right? And we represent them with these Greek letters, the mean and standard deviation. Okay. That's what happens when you take like a population distribution that's normal and convert it to the standard normal distribution. Okay. But you can also do this with samples, right? Notice that you are, no matter what, you're dealing with mean and standard deviation, right? Mean and standard deviation. These values, X bar and S, are the exact same things. They're mean and standard deviation, but these are actual statistics. Okay, because they come from samples, right? You're still doing the exact same thing. You're taking individual data points, subtracting the mean, and dividing by the standard deviation. It's just sometimes you'll see the z-score formula represented this way with the X bar and the S, and other times you'll see it this way with mu and standard deviation. Just know that it's the exact same thing. The only difference is that one is technically used for samples, right? Because we're taking sample data, right? So it may not be the exact true value, but it's as close as we could get, right? That's why we take samples, right? As long as you do them well, right? And you've followed all of your rules for experiments and you've conducted your experiment well, that you can take the sample data, which is much easier to obtain, and extrapolate it, right, and make inferences about the true values, right, the population values. Okay. No matter what, though, it's the same formula. Okay, whether you see it with statistics, like statistic symbols like X bar and S, or if you see it um, with parameter values, right? Like parameter symbols like mu and sigma. It's the exact same thing. Calculating a z-score is still always the data point, okay, which I'm going to go ahead and label over here on the right-hand side, okay? This here, ooh, terrible. Let's erase that. That arrow is ridiculous. Okay, the first thing is always your data point. Okay, minus, whether it's a statistic or a parameter, minus the mean, right? Or again, you can think of that as your true value. Usually we take average to mean our true value, right? And then divided by S, which is your standard deviation. Okay, same thing. Actually, let me turn that off and let me do this in a slightly different color. Okay, same thing, whether you're dealing with parameters or if you're dealing with statistics, it does not matter. Okay, so give me a second to clear my screen off here, and I'm actually going to show you this like in action, right? So I'm going to take a distribution, right, like a normal distribution, a bell curve, and show you how it converts using a z-score to the standard normal, right? So I will see you back here in just a moment. Okay, so what you'll see on the number line there is I drew a standard normal curve, okay? So it's centered at 0, right? Its mean is here at 0, and it has a standard deviation of 1. So most of the data in a standard normal curve can be captured within 3 standard deviations of the mean. So I kind of started over here at -3 and created a bell curve, something that looked kind of symmetric, right? And then ended here at +3. Okay, so 3 standard deviations to the left of the mean, 3 standard deviations to the right of the mean. Okay, then I'm going to draw on here another normal curve, but this one has a mean of 3. So my data point starts here at 3, and it has a standard deviation of 2. So that means my next little point is going to be 2 up. So 5, then go down to another 7, and then the last 9. So this one has a much larger standard deviation, so it's going to be much more spread out. Okay, so I have going over 2 to the left now, 2 more to the left, and I'm trying to kind of put these points at about the same location so that my curve kind of looks like a curve. Okay, so here is my curve number 1. Okay, so my goal is to get this curve, the one in purple, to look like the standard normal curve. Okay, so the first thing I'm going to do, and I'm going to change my color so that it's like in the same kind of family, but not quite. Okay, remember when you're doing a z-score, the first thing you do is subtract the mean. Okay, so if I take this curve and I subtract 3, that means I'm going to move it 3 units to the right. Okay, so I'm going to take this and I'm going to move it 3 units. Okay, so now this point, which was originally at 3, is now at 0. This point that was originally at 5 is now at 2. Right, so you can kind of see like where I'm going with this, right? These are all moved 3 spaces. Okay, so same shape, right? It's still really spread out. We just moved it a little bit. I'm really trying to make these as even as I can so that when I draw it, it looks like the same curve. Okay, so now we've just taken it and shifted it. Okay, then the very last thing that we have to do with it is, because it's too spread out, it's in the right location to be the normal curve, but it's too spread out, so we have to take it and shrink it. Right, so we're going to take it and we're going to shrink it. Right, and we're going to shrink it by a factor of 2. Oops, hold on. Right, and the way that we do that is by dividing. Okay, so when we divide, my new final curve, right, is right on top of the normal curve. Right, and so now, if you have all of your values as z values, we can actually use all of the tools that we have at our disposal for the standard normal curve and calculate a bunch of probabilities about this very random normal curve, right? That we couldn't before because it was not the standard normal. Okay, so give me a second. I have to clear this off because I'm going to do one more example for you that shows you a different kind of shifting and a different kind of transforming. Just give me one sec to clear this off, and I'll be right back. Okay, so here's our second distribution that has a mean of -6, right? So it's centered here at -6. You can see it in green. And then its standard deviation is 1/3, okay? So meaning, right, since I'm supposed to fit 3 standard deviations between the mean and the tail, right, the mean and each tail, So each one of these little dots that you can kind of see represents like 1/3, like a distance of 1/3. Okay, so when I'm doing a z-score, the first thing that I'm going to do is I have to subtract -6, right? But when you subtract -6, that becomes adding +6, right? So I'm going to take my distribution and I'm going to shift it 6 units to the right. Okay. Um, so when I do that, right now my new mean is at 0, but it's still this really skinny, like this really, really skinny looking distribution. My mouse did something crazy there. So it's kind of writing over my standard normal. But see, it's still this really skinny, skinny distribution. So what I have to do now, right, is I have to take it and I have to, if I'm dividing by 1/3, that's the same as multiplying by 3, right? So I'm taking it and I'm going to enlarge it, right? So I'm pulling this blue tail out here so that it fits right on top of my standard normal curve, right? And as soon as it sits on top of my standard normal curve, I can use all of my standard normal tools, which you're going to learn about more in the next section. So there's like a Z table, and there's a bunch of calculator commands that you can use to find probabilities. So I can figure out how likely it is that a certain data point occurs in that distribution, or I can figure out how likely is it that that I get a data point that falls between one endpoint and another endpoint, like one data value and another data value. I can figure out what my IQR is for that distribution, and there's a lot of other things that you can calculate. Okay. Remember that essentially what you're doing here is you're taking X values, right? So these here are all X values. Once you convert them to the standard normal, they are Z values. But the relationships between the values stay the same. The distribution is the same. You're just changing what it looks like. You're moving it around and either making it like skinnier or enlarging it. Right. So that is it for this unit, right? And in the next, not in for this unit, for this section, and in the next section, I'm going to talk about actually how we use this stuff and z-scores and all that fun stuff to calculate probabilities and figure out how likely something is to occur in a normal distribution. So I will see you all in the next video. Bye, everybody.